So welcome, guys. Thank you for joining us. We are going to do a short presentation today on pre-stressed concrete tanks, D110 tanks to be specific. Should be about 30-35 minutes, and I'll leave some time for questions at the end. If you guys have any questions during the presentation, feel free to interrupt me and we can stop and discuss anything you see in more detail. So a little background on myself. My name is John Henry Fisher. I am the district sales manager for the mountain region for Preload. That basically includes the mountain time zone. I've been with Preload for a little over 2 years. Previously to holding this role, I was handling all of Preload's industrial sales and private clients. That is kind of the world I came from. I spent 5 years in the industrial and refining divisions for mostly a company called Marathon, you might be familiar with as the gas stations. I worked as a mechanical engineer at an oil refinery for quite some time before coming to Preload. Preload is headquartered in Louisville, Kentucky. You'll see 2 names on the front door. We also share ownership with our sister company, Caldwell Tanks. They do ground storage steel tanks and elevated water tanks. Behind our office building, which you can see in that sky view, the green building is our office building, and behind that is our shop where we support our field crews of both the steel tank side on Caldwell and concrete side on Preload. Little history on Preload. The company was established in 1930. Built its first tank 2 years later in 1932. We have built a little over 4,000 tanks worldwide, but 99% of those have been stateside. We've constructed tanks in every state except for Hawaii. If you guys hear of a job in Hawaii, please let me know. I want to go. A little bit of history on D110 tanks in general. It began with the Type 1 tank. This was a cast-in-place concrete core wall with a turnbuckle winding machine to perform the pre-stressing operation. In the 1950s, shotcrete or gunite at the time was presented to the market, and we began constructing tanks by hanging a steel diaphragm and building out that core wall with an entirely shotcrete design. In the 1970s, Preload pioneered the advancement from the Type 2 to the Type 3 tank era, which is similar to the Type 2, but instead of an entirely shotcrete core wall, most of the core wall is precast on the ground and then raised into place. This provided a higher level of quality control and improved safety measures to the construction practices. And that's the same type of tank that we are constructing today. The codes and standards which define pre-stressed concrete tanks that Preload builds are AWWA D110. There's a couple ACI codes, 372 and 350, that have references to AWWA D110 as well. And NFPA 22 is for fire water storage tanks where applicable. This is kind of a swath of the different types of tanks we build. From top left to bottom right, we have a fire water storage tank in an industrial setting. This was for Valero Refining in Texas City, Texas. Middle top is a flagship project for Preload, largest pre-stressed concrete tank project to date, 3 22 million gallon reservoirs in Baltimore, Maryland. We just finished this project up last year. It was a 2.5 year endeavor. The top right picture is an equalization storage tank. The nice thing about this is it kind of details the fancy facades we can do if image is something that's sensitive on a project of yours. Bottom left is a clear well in Lubbock, Texas. As you can see, we can partially or fully bury our tanks. They can accommodate differential backfill as well. In the bottom middle, we have a package plant in Corpus Christi, Texas. This was an open top tank that can accommodate a lot of aftermarket equipment. So that's something we're capable of. And then we also do thermal energy storage tanks as well. This is for primarily chilled stratified water in large campuses and facilities, sometimes data centers as well. We incorporate the skills of both Preload and Caldwell to produce liquefied natural gas tanks as well. This is something that isn't super applicable to the group today, but I just wanted to touch on it as something we do as well. Now we're going to move into sort of the meat and potatoes of the presentation. It's going to follow chronologically the construction process of a D110 tank. It includes 4 major components. That's the foundation and the floor, the core wall, the dome roof, and the prestressing process. I apologize. I need to move this bar around. There we go. All of your faces were covering about half my screen. So before we get into that, I just want to go over kind of the working principle of a pre-stressed concrete tank. The idea is to build the structure and then single wire pre-stress it in a fashion that applies a force that mirrors the hydrostatic force that the interior of the tank sees. So we're going to single wire pre-stress it, and you can see in the diagram on the left, the distribution of that force is not necessarily the same all the way down the tank wall, but rather gets greater as you get lower on the tank wall. This pre-stressing operation places the concrete in permanent compression, which has a number of advantages. It reduces cracking, maintains water tightness, and increases the long-term durability of the tank. It also allows for free-spanning dome roofs. It allows for a pinned floor-to-wall connection rather than a fixed one, and it optimizes the required materials to conduct the job. I love this old ad. It's from the 1940s Municipal Index, and it's a Preload ad. And the great thing about it is our value proposition to the customer is the same today as it was back then. Economical tanks, no corrosion, no painting like a steel tank, and built to last the longest out of any water storage structures. So the foundation and the floor, this is a great rendering to kind of show the bits and pieces of it. Working our way from the bottom up, we have a leveling base. This is a fine aggregate stone. In Texas, they call it a 57 stone. Where I live up in Colorado, sometimes it's a 67 stone. But it's basically just a fine aggregate fill that's laid down with a high tolerance for leveling. After that, we pour a monolithic floor, monolithic just meaning a continuous pour with no construction joints. Typically, this is 4 to 6 inches in the center of the tank, and exterior to that, around the circumference of the tank, we have a thickened footer that's typically 15 to 18 inches. On top of that footer sits a neoprene bearing pad in between the bottom of the core wall and the interior curb and the top of the footer. You will also notice that there is an embedded PVC water stop. Can you guys see my cursor on the presentation?
Yes.
Yes, we
Okay.
can.
So right here is this integral PVC water stop. In the bottom half, it is encased in the floor, and the top half it's encased in the interior curb. That just prevents any leakage between this floor-to-wall joint, since it is a flexible connection that can swell and shrink a little bit as the tank is filled and emptied. This is what an excavation sketch looks like for a typical tank. We have a cut and fill with a structural fill that's shown in the diagonal hash section. Typically, this is 3 to 10 feet of cut and fill. And then once again, that 6-inch leveling base on top of that before the concrete is placed for the floor of the tank. We can do tapered floors and sloped floors to accommodate draining. We also do conical floors for accommodating clarifying scraping mechanisms for wastewater treatment applications. And in addition to these membrane floors, we can also do thickened structural floors to accommodate auger cast piles, drilled piers, rammed aggregate piers, rock anchors, things of that nature. But this presentation doesn't go into that because of just time constraints. So if you have any questions about that, feel free to contact me, and I'd be happy to get you some more information on it. This is what that leveling base looks like going down, and we use a compaction method biaxially, very similar to a mat foundation for a building. The next set of photos kind of walks you through what this forming process looks like on the floor. We have mild reinforcing here. You can also see this cantilevered forming has the PVC water stop hung around the circumference of the tank. So it's hung in place and then the floor is poured. This is that job in Lubbock, Texas. Typically we start our floor pours early in the morning when wind is settled down. Conditions are typically more moist, temperatures are a little cooler for the crews, and finish our pours into the day. We work with local concrete suppliers and pumping truck suppliers to get all the necessary concrete. Very seldom, but sometimes we do have construction joints in our floors for very large tanks. It is allowed by the code. And typically that is only driven by lack of concrete supply that we can get to pour the floors monolithically. We're going to start a video here. It works great in person, but sometimes over Teams and WebEx calls, it's a little bit grainy. So I apologize if it's not showing up very clearly, but this is what that process looks like. This is a small tank in Grand Lake, Colorado. There's going to be another video showing the erection of the walls of this tank. This is a 500,000 gallon tank. It's on the smaller side for preload, but great for educational purposes because everything happens fairly quick. Yeah, go ahead.
Yes, thank you, sir. Bye-bye.
Thank you. Bye-bye.
You can also notice the underslab piping for the inlet, the outlet, and the drain. Typically, these penetrations come up through the floor because if they come in that fashion, then they're not having to displace pre-stressing wires through the wall. If that doesn't make sense now, it will by the end of the presentation. Anybody have questions about the floor and the sub-base design before we move along to the core wall? Okay, so you're looking at a rendering of the core wall now. You can follow this kind of from the inside out. We have a precast concrete core wall with mild reinforcing steel. This is a minimum of 4 inches thick. Exterior to that is a carbon steel diaphragm that's mechanically seamed all the way around the circumference of the tank. Exterior of the diaphragm, you have your single wire pre-stressing encased in shotcrete with an architecturally finished shotcrete cover coat. Our core walls are 4 inches thick minimum. As tanks get bigger and taller, we thicken that core wall as necessary. And typically they're also tapered from the bottom to the top. So the bottom might be 8 inches, tapering to a 4 or 6 inch thick core wall at the top of the tank. We cast these core wall panels around the circumference of the tank like you see here. We lay that diaphragm down. We have a forming process around that. We lay our reinforcing steel, and then we bring in concrete to finish off the construction of each panel. We lay a sheet of plastic on top of that, and then we use a kind of a jump forming process to stack the wall panels on top of one another. The purpose of this is just to save the amount of space required to construct the tank. As you can imagine, if every core wall required individual casting bed, our construction footprint would be very large. So this consolidates our necessary footprint. Typically, the limiting factor is guys are just not tall enough to strike off the concrete as it's being poured after 3 or 4 panels tall. So 4 panels is about our limit. This is what it looks like once those forms are pulled off. You can see that carbon steel diaphragm is extending out of the edge of the core wall. That's intentional. And as they're erected into place, those extensions are going to overlap. We're going to seam them together, and then we're going to fill that gap in with a flowable shotcrete once the rebar has been welded together. This is what a typical construction layout looks like for a pre-stressed concrete tank. In this case, it's a 4 million gallon ground storage tank. We have our panel casting beds shown in the rectangles with X's through them. And then we have 4 crane locations. This is not 4 cranes required to do the job, but rather 1 crane in 4 different locations. And the purpose of that is just so that we can rent a smaller, more economical crane to get the job done, rather than renting 1 big crane that stays in 1 location and has the necessary lifting capacity and reach to do every panel from 1 location. We can also cast the panels on the ground of the tank, the floor of the finished tank, and erect them into place if real estate is very tight on the construction site. This is sometimes popular for buried tanks. This was also done on that tank I mentioned in the beginning of the presentation that was done for Valero refining. It's not the most economical and fastest way to do the job because, as you can imagine, you have to wait for the floor to cure before we can pour the wall panels on top of it. In a typical tank construction, we're beginning the casting and curing of the wall panels as the floor is being cured. In this case, we have to wait 7 days for that floor to be water cured before we can even begin the construction for the wall panels. In addition to that, the tank is really going to be designed to withstand the weight of the crane lifting a panel during the construction process. That's going to be the most stress it's ever going to see, rather than just being designed to withstand the water head height that it's holding. So it's a little bit excessive on the design standard for the tank. This is another time-lapse video of those walls going into place. If you've ever seen tilt-up construction for a large storage building, like an Amazon warehouse, this is basically the same thing, but we're just doing it in a circle with these precast panels with the diaphragm on the exterior of them. You can see the guy going around in the scissor lift, seaming those panel joints. And you'll also notice that the crane is going to lift one out of sequence into place right there with a temporary wall manhole. This is necessary for removing all of the interior knee braces and scaffolding once the dome is completed. You'll also notice the seismic cables exterior to the tank. We do design all of our tanks to the necessary seismic requirements given the local conditions. After the walls are erected, we pour the interior curb to encase the top half of the water stop. On the left-hand side, you can see what that looks like in real life application. On the right-hand side, you can see the rendering of what that looks like. After the interior curb is formed and poured, we move on to the dome erection process. So after this, we will erect an interior shoring system like you see here with concentric rings, working our way out to the exterior wall of the tank. I still don't know why on this job they put the scaffolding system up before erecting the walls, but it's a great tool to show you guys what this looks like without the walls inhibiting the view of the scaffolding system. Then we put a ribbing system from the exterior to the center of the tank and put plywood on top of that to finish the forming process. Then the dome is poured in a very similar fashion to the floor. It also has mild reinforcing steel underneath it. And instead of doing it in strips, it's done more in pie slices to work our way around the tank and finish the dome roof. It's what it looks like when it's finished. This is once again that job in Lubbock, Texas, that half-buried 8 million gallon tank. We also do precast domes. So in a similar fashion to how we cast the walls around the tank, you can see the dome panels being cast in the bottom right hand portion of this picture, and a crane erecting them into place, and then we would fill in the joints with a concrete pumping truck. This method typically works much better and is more economical in smaller tanks. And then as the diameter grows past 70 or 80 feet, there's an inflection point where cast in place tanks or domes are more efficient. The dome, obviously, once it is cast, imparts a hoop stress on the top of the core wall. You can kind of see that represented in the green arrows here. So in addition to the pre-stressing wire being tapered and getting greater in force as you work your way down the tank wall, it also has a very dense and high load of pre-stressing wires in the top portion of that tank wall where the dome connects to it. What this does is it places the dome in permanent compression, and it allows the dome to be free spanning. This is important to have no interior columns because you have a more efficient tank design, less man hours to construct it. You have no inhibiting factors for operations when they drain and clean the tank, and you don't have localized forces on the floor causing a thickened floor or a post-tension floor to be required. We typically do free spanning domes up to about 300 feet. Our engineering department says that they think they're capable to about 360, 375 feet of diameter for a free spanning dome. They're only 3 inches thick at the top, and they taper down to about 6 inches at the edges where they connect with the top of the core wall. Dome roofs are the most popular in our tanks. We also do flat roofs and open top tanks, obviously, but dome roofs seem to be the most popular for obvious reasons. They shed rainwater well, they don't crack, and they don't develop relaxation and slump to allow water pooling over time. Any questions so far? We're going to move into the pre-stressing operation, which is the final kind of quadrant to round this tank design portion of the presentation out. Okay, so pre-stressing, we have 2 methods for pre-stressing. On the left-hand side, we have a trailer mounted and tractor propelled system. On the right-hand side, we have a gondola mounted self-propelled system. The biggest difference between these two, other than the fact that one is on the ground and one's hung off the tank, is that the tractor propelled system on the left-hand side can apply 2 pre-stressing wires at one time, whereas on the right-hand side, we can only do 1 at a time. So on the right-hand side, we typically only use this method when we're really tight on space to construct a tank and for smaller tanks. The left-hand side trailer mounted tractor propelled system is by far the most popular, and it's much faster to construct the tank because you can apply 2 wires at a time. Makes a big difference when you're going around the tank a couple thousand times to wrap it. The process here involves placing the wire, maintaining wire spacing, clamping the wire as required when we run out of spools. We also confirm the wire stress, which I have a slide to show how we do that here in a couple. And obviously shotcrete encasement and a final cover coat when the tank is completed. This is what that pre-stressing wire looks like. It's a high tensile steel, a little over 200,000 KSI, typically a 6 or an 8 gauge, so it's a little under 1/4 inch thick. This here is on the dome band of the tank, so that's kind of the density of the pre-stressing wires that you can imagine goes into that dome band section to resist the hoop forces that the dome imparts on the top of the core wall. This is the tool that rides on the tank wall. You can see some grooved wheels that allows it to ride in the previously spaced wire, and then that center hub is adjustable to maintain the spacing of the next wires that go on the tank. It's another video here kind of showing that process. What's happening is we are showing 1 spool of wire going through a die drawing process. Through that die drawing process, it's placed in tension, and then that pulley system I showed you places the wire onto the core wall. These pre-stressing wires typically are applied at a force of 1,200 pounds per foot, and we swap different dies in this yellow arm to get different tensions. We can also use different wire, 6 or 8 gauge, and by adjusting the spacing as well. Those 3 tools allow us to get the distribution of forces that is desirable for the tank design. Right here is how we verify the stress in the wire. So this tool has a hook at each end of it and a plunger in the center. We depress the wire a set distance. In that plunger is a load cell, which measures the force it takes to do so. At this point, we know the force to deflect the wire a set distance, and we know the mechanical properties of the wire, and we can back calculate the tension in the wire. So we do this periodically in alignment with the plans and specs for the project, and document it to verify that the tank is being pre-stressed in an accurate fashion. The free body diagram of what that looks like. Happy to share that if you guys are curious. This is what a wire winding schedule looks like. So the important part about, there's a lot of information here. The important part to take away from this is that the pre-stressing operation is not done in one pass, but rather multiple phases with intermittent encasement of pre-stressing wire along the way. The numbers in the boxes represent the number of pre-stressing wires per foot of tank wall. You'll notice a gap from 2 to about 5 feet all the way through these phases. That's because we have to displace those pre-stressing wires for the wall manhole on the tank. This diagram shows what that iterative process looks like of pre-stressing wire with shotcrete encasement. The shotcrete really is there to provide a protective layer over the pre-stressing wire to prevent any long-term corrosion of the pre-stressing wire. Although it does provide some structural integrity to the tank, its primary function is to be a protective coat. Construction schedule for a 1 million gallon tank is about 12 weeks. The rule of thumb is every additional 1 million gallons is about 2 more weeks. A 1 million gallon tank takes about an 8-person crew, 8 hours a day, 5-day work week. And that includes management as well. This rule of thumb for 2 weeks for every additional 1 million gallon is pretty good, but as you get into very large tanks, such as anything over about 10 million gallons, this rule is not perfectly linear. So we can work with you on any project you have to develop project schedules and estimated durations for different activities. As far as quality control goes for D110 tanks, we have 2 types of quality control. We have concrete and material testing, and then we also have checklists. What you're looking at here is obviously material testing. We take cylinders from each batch of concrete used for tank construction, typically 5 cylinders with compression tests on them at 3, 7, 14, and 28 days. That leaves 1 cylinder as an extra just in case. We also take slump and temperature when they arrive on site and test for air entrainment. We're very particular about our concrete mixes, and we commonly turn trucks away if their mix designs do not meet the specifications required for the job. In addition to material testing, we also have a cloud-based system called FTQ360 that documents a variety of checklists which the project managers and project engineers own on the job. They have to complete these before they can move on to the next stage of construction activities. As you can see, this was halfway through last year. We had taken nearly 20,000 pictures on site to document quality control for each of our jobs. Tank maintenance, we kind of touched on this at the beginning of the presentation, but the value proposition of wire wound pre-stressed concrete tanks is that they have lower inspection costs over the life cycle of the asset. There's no exterior paint required. There's no exterior or interior blasting. Interior coatings are optional. Typically, they're cheaper if they are used, and they require less preparation to apply. So as you can see, over the life cycle of the tank, you gain back a lot of value when compared to competing products like welded steel. Another nice thing about type 3 tanks versus other types of tanks is you have a single source of responsibility for the tank design and construction. We certainly work with local engineering firms to help develop projects, plans, and specifications. But once the tank is finished, Preload has done the shop drawings. They have stamped them for the design. We've done a geotechnical review. And then our crews are the ones going out into the field, traveling the country, and doing all of the tank construction. That includes coatings, paint, and accessories as well. So if you ever have a problem with the tank down the road, you don't have a situation where the group who constructed it might be pointing fingers at the group who designed it, and any trouble knowing who is responsible for a defect in the tank design or construction. This presentation has some seismic considerations at the end. I don't think this is super applicable to you guys, so I'll go through it fairly quickly, but our tanks are designed to all seismic conditions. The base cables are situated exterior of the carbon steel diaphragm, but interior of the prestressing wire, and they resist any sloshing and horizontal shear forces in the event of an earthquake. This is what it looks like both on paper and in practice, and you can show a little enlarged view here. They're half encased in the floor, similar to the water stop, and then they get the top half encased in the wall, sandwiched between the interior diaphragm and the prestressing wires and shotcrete that are exterior to them. And that is the end of the presentation. If anybody has questions, I'd be happy to stick around and answer them, or dive into any of the topics we talked about during the presentation in more detail.